Welcome everybody to the second deep learning theory seminar of the semester, and the first one which is recorded. Right. So today we have like the great pleasure of having Mario Ullrich join us. So Mario is a numerical analyst and a complexity theorist. Depends how you an information theorist, depends to many hats and very prolific research in a bunch of areas. I've come across his papers personally. A lot recently, looking at sampling numbers and all kinds of different notions of complexity. But this paper also, of course, naturally caught not only my eye, but I thought it would be very interesting for many people who attend this seminar. This is pretty fascinating. So Mario will be talking to us about a Riesz basis of deep neural networks. So basically kind of fusing classical approximation results or techniques into, I guess, neural network approximation theory, and actually come up with very clean proofs for statements which usually are very messy. So it's very nice. And just a quick word about Mario for those who don't know him. So Mario completed his PhD in 2012. Right, and so my German is very bad, so excuse me for the pronunciation. At the Friedrich Schiller University, and he's done many things since then. But let me just say maybe the two things right now. Currently, so Mario right now is an assistant professor at the University, Johannes Kepler University in Linz, and he's in the analysis group. And I just saw, just that he finished his habilitation. So that's exists in France and Austria in 2023. And since then, I mean, he's active on a bunch of journals. I think he's one of the only other people at JMLR doing approximation theory, so that's really great. There's so much to say about Mario, but instead of taking a time to talk about how amazing Mario is, which I generally think, maybe I'll go right into the talk. So after you.
Thank you very much for the nice introduction. So I think this was exactly what Anastasia told us. It was precisely part of my introduction, except the good things about me. So I'm more coming from the approximation theory and more from the not so applied stuff. But clearly, neural networks are everywhere, and we want to understand neural networks. And at some point, that's why I use this title, making neural network analysis more easy. We try to understand when you try to understand proofs of approximation rates, optimal approximation rates, then that's often a big combination of a lot of different inequalities, a lot of different techniques that you use to tackle high-dimensional scenarios, especially. And this is kind of in contrast to classical approximation theory. Think of Fourier series, right? If you consider Fourier series in one dimension or Fourier series in high dimensions, who cares? If you consider it with another orthonormal basis, more or less, who cares? The techniques stay the same and so on. But this is was completely different for neural networks. And I want to explain a little bit what we have contributed to this picture. And what I think is maybe you don't learn any new result. Maybe several of these results have been, I will highlight that at the end, what is really new. But I hope that the proof technique we basically invented by that could be at some point kind of standard to teach it, and also to prove kind of universal approximation theorems, at least in some simple settings. Okay. So the first slides of a neural network talk I learned always have some biological and artificial neurons on them. So I also do that. But you have seen that often enough. You don't need that from me or what this is, just for the slides to be nice. And these pictures were created by my co-author Cornelia, and I want to show them. The same way, you have some kind of activation functions. You also, again, you know that. During this talk, I will only talk about the ReLU activation, which is the simple one, maximum 0 and x. I know that probably by now people use different things in applications, but that's a beginning. And I very much hope that the stuff I show you today can be extended a lot to other activation functions and so on and so forth. Okay, so yeah, we consider only the ReLU, piecewise linear, kind of default activation function for many. What is a neural network, or precisely a feed-forward neural network? It is given by a number of affine mappings, so just a matrix applied to a vector plus another vector. Then you concatenate them. You take a affine mapping, you take an activation function, you take an affine mapping, you take an activation function, and you just do that L times. Okay? So L will, for me, the depth of the network, and W will be the width of the network. So to say, how many neurons you have per layer. So these guys are called layer. How many neurons you have there. Okay, so this is the definition of it. And from now on, you won't see complicated formulas like that. So maybe that's yeah, it gets easier by slide by slide. So what we need more during the talk is this kind of epsilon WLD. I realized while preparing the talk that I'm not sure how you pronounce this letter in English, because for German it's close to epsilon, which is our y. So epsilon is completely fine for me, but do you call it epsilon also in English?
I think it's what it's called, but at least as someone from Greek background, it always makes me cry.
Okay, I'm sorry. So I will use epsilon for it, just because it's how we call it. So this is the class of all functions on RD. So they get the input parameters, put a number, and they can be produced by a neural network, as explained here, with a specific width and specific depth. And that's the W and the L here. And what is clear just from the definition, everything is affine, the activation function is continuous and linear and so on. So if you take the ReLU function as an activation function, this class is a subset of continuous piecewise linear functions. That's more or less all we need. So let us take a simple example, and we need that example during the next slides more extensively. So let us consider the head function, for example, right? It's just this simple head. And what we can do after a little bit of case distinction and trying out, see that this head function can just be written as a neural network of, in our language, of depth 1. So there's one hidden layer, of width 2. So there are 2 neurons in this hidden layer, right? And this is the precise formula. I guess you, yeah, one can find that everywhere, just as an example. So what else? What else is these kind of classes have some nice properties, but have some also bad properties. Let us start with the nice ones. The nice ones is if you already have some ReLU neural networks, then you can have 2 of them. It's comparably easy, structurally easy to compute the composition and to compute the sum of them, right? So just building a network and stack them on each other. I will make a picture a little bit later, but more or less you know how to do that. It's just concatenation is just put them behind each other, and the sum also clear. Okay. The bad news is that the ReLU activation function has problems calculating a product. We will come to that in the high dimensional setting a little bit more. And the reason for that is completely simple. The product of 2 numbers, even though it is for every fixed number just linear, it is not, as a 2-dimensional function, a piecewise linear function. So there is no way to represent this kind of function exactly. And so the typical way of handling these kind of products is then you use a network to approximate the product and then use this approximation and continue, right? But from my point of view, this might already be the first kind of mistake, because we know what our building blocks are, and our building blocks are neural networks. They are piecewise linear. So there must be kind of an easier basis, an easier way to work with these things, completely avoiding the product. Okay. So this is the question. Can we find an orthonormal system that's more difficult, but a near orthonormal system which just consists of neural networks, right? And we want to do that in high dimensions, not only on the line, we want to do that in high dimensions. Is there something like that, right? And this problem was already studied by some famous guys. So Ingrid Daubechies, DeVore, Simon Foucart, Benjamin Hanin, and Petrova, I forgot her first name, whatever. So these 5 guys in the paper Nonlinear Approximation, 4 years ago, they produced a system of piecewise linear functions which resemble the trigonometric Fourier system in 1D. So what is it? It doesn't look like a very deep idea, to be honest, but it seems that was overlooked or whatever. No one really studied it. Maybe there was no reason for it, whatever. What you just do is you take the sign take the cosine, and you just make them piecewise linear, and then you analyze these functions, right? So in this case, these are the two functions I plot here. You see, I take something that looks like a cosine, just I'm linearly combining the extreme points, so to say. The same with the sine function, right? So these functions are kind of simple. You see how you can write them with the help of an inner product, of an absolute value. And since we want to work with them as they would be sine and cosine functions, we just periodically extend them. Let me say that this is tricky for the following reason. A function on R, which looks like this, like it is here, has infinitely many breakpoints, which means those functions here cannot be represented as a neural network. But we will see that is not a problem. Actually, we cut off at some point and we don't really care what's outside. So we only use these functions inside of a proof. Okay. Again, cosine and sine. What would you do with the sine and the cosine functions, or with the trigonometric, with the e to the I, k, whatever? If you want to get a higher frequency, you just put the k inside. You don't do anything around that. You just make, instead of taking the cosine of x, take the cosine of k times x. And we do the same with these functions. So we just define kind of the scaled versions of these piecewise linear sine and cosine functions. We just find them like this. Okay? We just write a product here. And now kind of the magic comes. Let me first, a few properties. So as I said, they resemble trigonometric functions. So this is the picture from before. There are some scaled versions of it, right? Just no magic. The cool thing is that they share a lot of properties with the original trigonometric system. So for example, you can know that the sine is just a shifted cosine, right? Funny thing is, the same holds for the sine and the cosine functions, this piecewise linear case, but you need to be careful a little bit with the shifts. The property here is essentially the same. You can bring both functions, you can bring one function to the other function, which is so technically makes some things much easier, right? And second interesting property is, if you consider this scaled linear cosine, where the frequency is a power of 2, you can represent it exactly by the head functions I discussed with you in the beginning, the cosine function at the end. So you just take head of x, then head of this, and so on and so on. You take that, this kind of increases the frequency, and at the very end, you apply cosine. Which means we can build higher frequency piecewise linear cosines as a concatenation of easy neural networks, which means it is itself an easy neural network. Okay. If k is not a power of 2, you have to do some kind of different trick. It is essentially the same. So what we get out of this is that ck and sk, as I defined them for you on 0, 1, can be easily reproduced in ReLU neural networks. The ReLU neural networks are of this size. So you only need width 2, so they are very thin, not shallow, but thin, right? So they don't have many neurons, but you need some deepness. They must be at least log k deep to get the required frequency. Right? So now we have building blocks, and these building blocks are, as I said, are quite deep but thin. Okay, that's all we need from these things. What is the magic about those guys? Magic is that if you take these univariate functions, as just explained to you, then they are Riesz bases of L2. What does it mean? A Riesz basis means that every L2 function can be written as an infinite sum of this type. We have convergence in L2, so every function is in the closed span of these set of functions here. And in addition, you can count the L2 norm of a function if you only know the coefficients. Okay. So this is first a good step in the right direction. So there are two things. I will talk about d-dimension in a second. The second point is this is only for L2, right? So it somehow in L2 all of these functions are in the same way important. This does not tell you in the beginning which of these functions are the most important ones. And if you are in L2 and if you just are having no smoothness, no regularity, and so on. There is nothing like the most important or the least important stuff. So you need to get some additional regularity to study something like this, and this will become in 5 slides or so. Okay. The second point is that's the was before our studies began, to study this in higher dimensions. As I explained to you before, if you have a so in higher dimensions, so a tensor product of 2 Riesz sequences is a Riesz sequence, which means using these one-dimensional guys and then taking tensor products of them gives you a Riesz basis. But the problem is then these constant here would explode, would just would come in exponentially. You do not want that. Somehow want to control the dimension, and having something where the exponential dependence on the dimension comes in so early in your studies is not, you want to avoid that, right? So yeah, that's the bad news I want to tell you, that the ReLU neural networks are complicated to calculate with products. So also tensor products as considered here. So which means there are many problems with this technique. And so, which is sometimes I would call a local technique, because you usually do that by localization and then make things in small cubes. And this ends up with very big and complicated constants. And so we wanted to study non-local techniques. Okay, high dimensions. This was done by my 2 co-authors, Schneider and Vybiral, a year earlier, so now almost 2 years ago. And the possible interpretation behind this technique, which is kind of already nice, is that if you have the product of two signs, then you never need to computing the product of 2 signs, so the tensor product of the sign function with itself, you never need to consider a product. Why? Because we have something that we learned early in our studies, that's the trigonometric addition formulas, right? So look, that the product of 2 signs is just the same applying the cosine to a difference minus the cosine to an addition, and take some half here. Right? So in the second formula, there is no product anymore. And since there is no product, I explained earlier, those are much easier to work with if you then take the neural network versions of it. Okay, so that's the result. So if you want to take the high dimensional versions here, it's defined here, that's good. So for a vector k, we define this kind of ordering, so this kind of property, so this k plus bigger 0, it just means that if you take the vector k, then the first non-zero entry is positive. And that's only a way to say that for every k, for every vector k, we only need either k or its negative version. We never need both, because they just disappear. You need to take them away. Otherwise, they are dependent. Okay, and again, we take k times x, which is just this inner product of these 2 vectors. Then this system here is a Riesz basis of L2. This is kind of magic, right? Why? Because all high dimensional stuff that's going on, every instance of you never need any product here. You only take a times x, which is just a linear combination of all entries of x and all entries of k. Then you apply c, and this function c is just the univariate function we saw in the very beginning. It's just the univariate piecewise linear cosine and sine functions here. It's the only difficult part here. The rest is just linear. Okay, so this set here, then a Riesz basis of L2. Moreover, the Riesz constants are independent of the dimension. I will come to that back in slides, so that's important also for the higher smoothness case. But this is kind of magic. So this means this here is as close as it can be to an orthonormal basis, as you can imagine, because just it is all Riesz constants are independent of the dimension, and you can compute norms with it. You can do everything with linear combinations and so on and so forth. So that's a very good building block, right? Usually in classical numerical analysis, you take, as I said, a trigonometric system, cosine, sine, or polynomials or whatever, and work with them. And now we have this kind of building blocks also for neural networks. Okay. Let me say something about how to write them, because this will be important for the quantitative things, right? as I said, we have a Riesz basis. But this is about infinite sums. And if you think about Fourier series and similar things, then the next step would be we now consider partial sums of these Riesz basis terms. And these partial sums that you take, you need two things. First of all, each of the partial sums can be easily handled, kind of. I will come to that on the slide. And the second is you can approximate well with these partial sums. You would do the same in Fourier series. Okay. So now assume, so D is larger than 1. Assume you have some index set, which is a subset of ZD without 0. And a function that is written like this. So it's a partial sum of our new Riesz basis, right? This function is a neural network, can be represented as a neural network. You have two possibilities. We only write two. There are many more possibilities, but you have two possibilities to write it. So either you take a network that has a big width, so the number of elements here comes in the width. Then the depth of the network is only logarithmically in the largest frequency you see. Or take a network that is quite thin, quite thin again, but its depth then must be here. So each of these functions can be written in this way, and without, maybe you don't need to prove it, maybe the picture, you see more of that. So assume you have our building blocks. So these are just our CK and SK functions. You have some of them. And then you have two different ways of just combining these networks. You want to compute a partial sum, so a linear combination. So you combine them in two different ways. So either you stack them on each other, which means the new network has the same depth than before, than the maximum of all of those, but it is much wider. Or you stack them behind each other. If you want to do that, you somehow must be clear that the second layer here, second block, also gets the input. So, and for this, you need some kind of a source channels and collocation channels just to collect all the inputs and outputs for the different networks. So that's the two ways of stacking them. So these inequalities here will play a role in a minute when we come to quantitative bounds. Okay. So what about smooth functions? I told you already, this things with L2 is a very good starting point. We already know this is a good candidate. But now what we also need is that we understand what are the most important of them, right, in these particular settings. And the approach we took in our paper is the following. We started with the classical Sobolev spaces, so just Hilbert spaces of smooth functions. I never say something about derivatives here. I hope you know this kind of function classes anyhow. So we consider real valued functions on the unit cube, can be written as this kind of trigonometric sum here. And by the way, that it's real valued means minus m is the same as am complex conjugated or so, just for completeness. So you take these guys, and the norm in this Hilbert space is given just by the square sum of the coefficients and some weight here. So look, if you take s equal to 0, that's just L2, just the L2 space. And for larger s, you take some decay. You want some decay of the coefficients, where higher frequencies get a higher rate. Okay? And just as a try, why not? We define the same space because we already know that those guys, our CK and SK neural networks, we already know that they are Riesz spaces L2. So we just define the spaces like this. We take the classes that we call Fs, which are precisely defined as the Sobolev spaces with basically the same kind of norm here. But we now take linear combinations of our piecewise linear cosine and sine functions. So this could be understood as kind of a regular class of neural networks or so, right? We just define them. And now the question is, are they related? So what is the relation between these two classes, right? If we are lucky, then you can transfer one class into the other a little bit and so on and so forth. The answer is more nicer than I expected. These function classes are just the same. Right? It's just exactly the same set of functions. There is no function that can be written like this. It cannot be written like this, and vice versa. It can just be written like this, always. So these function classes are the same as long as the smoothness is smaller than 1. Larger smoothness is really not possible because the ReLU networks have kinks. and these kinks do not allow for derivatives. But if you consider these classes for small smoothness, then they are just the same. Okay. Again, in the sense of equivalent norms, and this system now, the Riesz basis. Okay, we do nothing else but some weight in front, because these guys do not have the correct norm. You want them to be normalized, kind of. So put some weight in front. So these are now a Riesz basis of the Sobolev space. What does Riesz basis mean? It means that if I take this kind of linear combination of our sk and ck functions, then the norm can be bounded above and below just by the coefficients. The same as we had for the Sobolev, for the L2 case, we also have for the Sobolev spaces for all smoothness smaller than 1. Again, that's the funny part here. Constants here, again, do only depend on S. They do not depend on the dimension. So also for smoothness classes, you can do exactly the same than I explained to you before, where the constants do not depend on the dimension. And to make some advertisement about techniques I have never used before, but the math behind, if you want to prove something like this, then what you are doing is you just write down the basis exchange matrix. So what is it to transfer one basis to the other? So that's basic stuff. And when you try to analyze this, then you realize that already the Kashgorian circle theory works. Not sure if you still know what it is. It means that if the matrix has its biggest entries on the diagonal, and all the off-diagonal entries are small, then you can control the spectrum of the matrix. Okay, and this was already enough. So it's a comparably basic method. But in studying these kind of sums that appear when you study the off-diagonal entries, Möbius function shows off, which is also kind of magic. So the Möbius function tells you something for a natural number if it has some prime power 2 or more. Okay, you have to check it on Wikipedia. I already forgot what it is. In any case, it's a very important function, and this function just shows off. Shows off if you compute these inner products, and then it's there, and then you can use kind of well-known results on bounds on infinite sums involving the Möbius function, which is again a little bit of magic. Yeah, we were greedy. We were quite greedy when we had the Sobolev results. So let us also do the. Anastasia, do you have a question, or is it a?
Oh no, just put a thumbs up because that was pretty cool.
Thanks.
Yeah.
Great. Yeah, so we were a little bit of greedy for the Sobolev spaces, and so we decided let's do the spaces that are more studied in the neural network community. And the reason is a good reason, and these spaces are much more suited for high-dimensional approximation. We will see that in a minute. So those are sometimes called Barron spaces, and are different definitions of Barron spaces in the world. And this is the one that's sometimes called the spectral Barron space or spectral periodic Barron space. One could just say it's some people from the classical function space theory call it Wiener algebras, weighted Wiener algebras. So one has to be careful that you use that you check what it is, because this is what you do is take the same sum, the same trigonometric sums. Now you define the norm just as an L1 sum, one series. Right? So instead of taking L2 norm here, take an L1 norm, a weighted L1 norm of the coefficients. And yeah, who could know that this class is so much better suited? I would not have expected it, but the results are drastic. Whatever, let's come to that in a second. That's the same strategy. Instead of considering the trigonometric sums with an L1 norm, we take again our piecewise linear cosine and sine functions, take again the L1 norm, right? And so everything the same, L1 norm instead of L2 norm. Maybe you are not so surprised anymore, but I can tell you I was surprised in the beginning. These spaces are again the same if you take smoothness arbitrarily close to 1. Okay? So again, equivalent norms. In this setting, it's an L1 Riesz basis. L1 Riesz basis means that norm in the class is given by an L1 sum of the coefficients. Again, constants are independent of the dimension. Okay. So this is was for me a little bit more surprising. Comparing the technique is comparably close, but instead of studying the spectral norm of the basis transition matrix, you study some other norms, some L1, L infinity norms or so. Check the paper if you're interested. Okay, so having this at hand, we now have Riesz basis. Let us continue with our journey through classical approximation theory and how we would do that. Right? So look at this. We now know what are the important CKs and SKs. We know how to write the norm. We know that every element in this Barron space or in the Sobolev space can be written as an infinite sum, and so on. We all have this classic stuff. So now what to do? We cut off the most important part and continue, right? So what is the most important part here? Most important part are the guys with the biggest weight, which means that are those close to the origin. And since we chose an L2 norm of the frequency, which is also up to debate, by the way, since we choose this L2 norm, the most important objects are balls, right? So which means the only thing we need to do now is we need to count the number of lattice points that are inside of a ball with radius r. Now you can do some computations, check for known results and so on. In our paper, we do some research, but I also think we improved some of the bounds a little bit in one of the regimes. I do not remember which one. So we know that the number of lattice points can be upper bounded depending on the relation between the radius and the dimension. Okay? So if the radius is small compared to the dimension, then it is exponential in the radius. If the radius is large compared to the dimension, then it's exponential in the dimension, which means it is always only exponential the smaller one, which is kind of important if you want to make some high dimensional studies. Okay? So in our case, if we plug that in, so we will use the inequalities in a second, just using this NRD here. If we have a function in the Sobolev class, we just have to choose R like this, absolute constant, so constant only depends on S, divided by epsilon to the power 1 over S. And there is a ReLU neural network, which has this function as an output, right? The width 4 times this number, and with a depth, which is just having R and the minimum of R and D in here. Such that F can be approximated this. Let me say it again. For every function in the class, we'll find a neural network which these parameters, which is a good approximation to for epsilon. Okay. Let's make a little bit more corollary because that's hard to grasp. What is R, what is D, what is epsilon, and so on. So let us make it more precise. So take S between 0 and 1, is a natural number, epsilon between 0 and 1. Then there are constants that only depend on the smoothness, such that F can be approximated by a neural network with an error at most epsilon. And we only need that the depth of the network is log 1 over epsilon. And the width is either of these quantities. Right? So now it kind of depends what you choose. Formulas are a bit complicated. They're a little bit strange. So first one says that if you fix epsilon, let's say machine precision, 10 to the minus 7, and you just lay, or 10 to the minus 42 if you want to, and let D go to infinity, then everything only depends polynomially on the dimension. Okay? So for fixed epsilon, you will always get a polynomial in the dimension complexity here. But of course, the exponent might be very big. Okay, so this is the case if epsilon is larger than this. So this is exactly the case I told you. If D is big enough, this is always fulfilled, at least if epsilon is fixed. The way around, if you don't care about the dimension and you now want to have the optimal approximation rates with epsilon, then you see that our results are kind of optimal in the width. There is this epsilon to the minus D over S. Here, L only grows logarithmically also. But this is maybe suboptimal, but again, that's a starting point for us here. Yeah, that's the one for Sobolev spaces, but you already see the optimal kind of order that you see here. So how it works, there is a D in the exponent, and you don't want that. Yeah, that's already will kill us. Also in the next chapter, small chapter where I talk about sampling, this will kill us, at least in the setting of using general results considered. So Barron spaces are much better, and I'm sorry for this overwhelmed slide. I'm myself a little bit overrun, so let us go through it a little bit slow. What is it, right? What are we doing here? So the quantity we need is the best n-term approximation error, right? This means, let's go slowly through it. Okay? Consider vectors v, infinite vectors v, which are weighted by our rate that we had before. Okay, so they are kind of in this unit ball of this rated L1 space, small L1 space. Okay? And now we want to approximate this v by a linear combination of unit vectors. So just take some of these entries non-zero, and the number of non-zero entries should be n. Okay, that's the small n here. And now we ask for the best we can do. Okay? So for every v in the L1 class, we take the best approximation error. So these quantities can be well computed. You will find that you can find that in our paper, but also elsewhere in one dimension that's easy to compute and stuff. So this is not a difficult object. But this number here is essential and gives us a clear shortcut in our analysis, kind of. Okay. So what is the neural network approximation in Barron spaces? Again, smoothness smaller 1. Then there are just two constants that only depend on S. No D dependence is hidden here. Such that if we choose R again as before, and we choose the small n, such that this guy is small enough. So this guy should be smaller than epsilon, say. Right? And again, this can be computed just depending on the rates. And for every function in this Barron class, there is a ReLU neural network with these parameters. So the width of the network is the same as the n for the best n-term approximation. The depth, again, is the same as before. Okay? Moreover, this neural network can be given explicitly depending on the best n-term approximation of f in the trigonometric system. Okay, I do not have a good shortcut to explain to you why this is so beautiful, except directly going to sampling. So let's forget for a second about best approximation and what I just did here with you. Okay, just for 2 slides. So what we actually wanted to, what I usually do, what my kind of research is I'm study what is the best I can do if I only have samples available. Okay, so far in this talk, I studied best approximation, and best approximation is clearly a natural benchmark. Okay, you give me a finite dimensional class, or you give me some class of easy objects, and I want to know what is the best approximation of a function in a bigger set around from this easy objects, right? So just the best one. So that's a natural benchmark, but in general, it's a different question than asking what is the best I can do with n samples. So if someone tells me I can compute n function evaluations, then this is not the same. So that's just a different subject, kind of. And that would be a completely different talk. So I'm not going too much into here. Maybe some selfish advertising. There will be an upcoming Acta Numerica article, which is called Approximation of Functions with Daubechies and myself, about 200 pages long, where we explain all of this. What our view on best approximation, optimal sampling, and so on is. So please, if you're interested, have a look. Okay, so the good thing with all this I discussed here, when I want to learn from samples, is that now we have a linear structure, similar as for Fourier partial sums or whatever, or polynomials of a given degree. So we have a linear structure, a linear space given, and finding the best approximation on a linear space is well understood if only samples are available. In contrast, if you consider neural networks, you really have to do it kind of case by case, because no one really knows how good samples are for neural networks, because the class of neural networks is extremely big. Okay? It's just too big to do things to understand it if you only consider then function evaluations and so on. I think there is a lot of stuff done, but getting something explicit in the dimension is a hard task. And okay, so for Sobolev spaces, for example, just to see we can use fundamental methods that are comparably basic from classical approximation theory. So for the Sobolev spaces, it's completely enough to take least squares. So yes, let me say it before, it is enough to learn your neural network by your least squares method. There is no need for anything more complicated, as long as your model set is a Sobolev space or something in this direction. More, you can just use an unweighted, just simple plain least squares method. As I show you here, or maybe that's too long, as there's still. I don't want to bore you too much.
Oh,
so
no,
that's the general.
There's time. Yeah.
Okay. So this is kind of a general result I proved together with David Krieg, and later we extended that with Katja Pucharska and Tino Ullrich, friend of mine, not related. And this is a general kind of result which comes basically without any assumption that is not needed to define everything that's on the slide. Okay, so assume you have just some set D would be the unit cube. You have a class of function, would be a Sobolev space, but more general. You have any orthonormal basis is uniformly bounded. That's the three kind of conditions you have. And if you define the first n of them, take the span, this kind of Vn, you know something about the best approximation error. So this is best approximation here, you see? For every f, take the best g, just measure the error in L2 norm, and then you take the supremum over the whole class. Again, just a Sobolev class. We only apply it in this case. If you know that this error decays like n to the minus t with the constant, this t is larger than 1/2, you can just take n least squares with n log n IID points. All of them are just uniformly distributed in the cube. Okay, so this is kind of a rather general result. And although this might look known or so on, believe me, it was not. It was not even known for the trigonometric system. It was already a problem there. But let me, again, that's a different story. So if you do that, then you get this kind of order of convergence, this error bound here from this. And you see, consider, let's say, approximation in L2 norm equal 2, you see this disappears. So it's just exactly the same order of convergence. Right? So for L2 approximation, you don't lose anything. For approximation in the uniform norm, you lose a factor, some square root of n. Okay, so you lose in the order of convergence 1/2. It is known that this is best possible. You cannot improve that in general. In the generality I state here. Okay? So this is a say up to the logarithmic oversampling we have here and up to the precise constants. This is an optimal result. Unfortunately, it's not very helpful for Sobolev spaces, at least not in higher dimensions. Why? Because I require that the best approximations for the given subspaces I define here, right? The best approximation is fast enough. It must be faster order 1/2. And for Sobolev spaces, we saw it earlier, order is S divided by D, and S divided by D is, say, rarely larger than 1/2. Except I choose S depending on D, and this would kill our earlier arguments, kind of, because then everything depends on D again. So this is not a good class for studying high dimensional problems, but still it's quite open, yeah, how good this can be done with the neural networks. So it doesn't mean that this is optimal for this neural network problem. It just tells you that in general it's optimal. Okay, so as said, Sobolev spaces are not quite interesting in higher dimensions. The order of convergence is too bad. The thing is different for Barron spaces. And this is what I want to explain to you on the last, say, 2 slides. So for the Barron spaces, one can use techniques from nonlinear approximation. And the classical method here is spaces Pursuit denoising. Maybe you know one of its variants, like lasso, right? So there are a lot of variants that are all doing approximately the same, coming from compressed sensing or so. Let's just say some buzzwords. So these methods are well known, and you can also implement them, I think, in quite some time. Okay, so and this is the method we consider now. Okay, so instead of taking just least squares, we minimize the B0 norm. So B0 norm is just the absolute sum of the coefficients of this guy G here. Right, so G is a function in our E-spaces decomposition. So we only take the sum of the coefficients, and this we want to minimize this object. under the condition that this square sum here is kind of small. And now there is the, I think, most beautiful result that we established. I'm not sure if you can value it already, but I like that very much. Okay. So for the Barron spaces, oh, this should be a title here. I used the wrong brackets or so. So you take, again, smoothness between 0 and 1, P between 2 and infinity, then there is a constant, an absolute constant, depending on S, clearly, but otherwise independent of the dimension, such that if you take capital N, be of this size, then the algorithm, the basis partial denoising I just showed you with this the specific value of R and the points just uniformly distributed in the cube satisfies this bound. Since again, a lot of playing around with everything, so let me rephrase that a little bit. In other words, this means with n samples and this basis partial denoising, you can do an LP approximation error in the worst case, which is of this order. The error is at most p divided by n and then some log term to 1 over p. And oh, this is bad here. This is really bad. There's no f on the right hand side. So you should be supremum and then I divide by this. Or forget about the supremum and think of for all f it holds. Also. Oh. So this thing here tells you the number of samples you need only has to grow linearly in the dimension. And maybe as the thing I'm proud of this, that's precisely the result that Barron proved in his paper 93 or so for the spectral, for his what is now called spectral Barron spaces. Barron proved more or less precisely this bound here, but only for L2 approximation and for smoothness equal to 1. So, and for smoothness equal to 1, the spaces here are smaller, right? So the larger the smoothness, the smaller is the space, which means we now proved that the result that Barron had never needed any smoothness. You never needed any derivative or whatever. It was already enough to take some s larger than 0. So the important aspect is nothing with smoothness. It is take the L1 norm of the coefficients instead of L2 norm of the coefficients. That's the important stuff. And I think that's a natural bound. So we extended that to other p larger than 2. You see that then the exponent gets bad. And yeah, everything else is independent of dimension. That's all I want to say. Thank you very much.
Oh, thank you. Actually, it's very, very cool talk and super well explained. Any questions in the audience? Okay, no. If not, actually, I had just like a pure curiosity question. Because many of the questions I guess I had in the paper and answered during the talk, which is great. Yeah, just like something that came to mind. So in the definition of like these Barron spaces, does anyone ever consider like other coefficient weighting, and maybe one can expect to have like really, really fast rates? Like, is this, yeah, basically like these powers, like yeah, because here you have some kind of like nuclear guy, like this L1 power, or at least, yeah. Do people consider other kinds of?
Yeah, sure. I think but I think if you make this p larger than 1, the results won't be that good anymore. I don't really know. For every p larger, smaller than 2, there must be something better. But I think the more interesting cases are even p smaller than 1.
Yeah, that's what I meant. Yeah.
That's what you mean.
Okay.
No, I'm quite sure there's stuff that can be done because all these Stechkin kind of inequalities. So there are some inequalities that are needed there to compare best approximation in different norms. For sure, things can be done there, but we didn't check now. I'm not so sure what's then but yeah, I think that's a good thing to do.
Cool. That was actually my main question. Okay, I had one more question, right? So I was trying to read my own writing, which is quite challenging. Yeah, this is a question for the very, very beginning. Yeah, so for like, yeah, for the respaces type results, yeah, in some sense, all the limitations on smoothness, like the S, is because of like you mentioned, the irregularity of the ReLU function itself, or like, piecewise linearity basically. Yeah, would you expect like such proofs could be like extended or generalized if you had like some kind of sufficiently smooth bump functions implementable by neural networks?
Since
Or
this
like,
is on since this is on my desk for a year, and Jan is also in the audience, I better say to everyone else, no, that's not possible to do.
interesting.
No, no, it is.
Okay,
It is
okay.
for sure. We were just too lazy by now, right? So
Okay,
we
yeah, yeah.
want to do that, and I think I'm very curious what the outcome is. I
Mhm.
really don't know. It's not quite clear. It's not enough to just take, say, some ReLU car
Yeah, yeah, yeah.
activation functions. I'm not sure if this is enough. I don't think so, but we will
Mhm.
see.
Okay, cool,
But
cool.
in any case, the analysis we need to do for the gram matrices then
Yeah,
is will be much more complicated. Of course,
yeah, of
that's at the
course.
or maybe not. Maybe when we start, it's done in some weeks. I don't know.
Okay, cool, cool. Yeah, actually, those are my main questions. But yeah, very, very cool talk, honestly, and nice to meet you.
Thanks.
So last chance for everybody else. Any questions for the shy people? Okay, I guess not. Okay, cool. Then yeah, I thank you again, and I'll probably see you worst case. Yeah, when I come